Hello to everybody. I'm Catalina Curcianu and I am the chair of the Dissemination and Communication Work Package within the Strong 2020 European project. And welcome to all of you to our new public lecture in the series of Strong 2020 public lecture series. I'm very thrilled of the today lecture because it brings us to the extreme in the universe. Before, however, introducing our speaker and leaving him the floor for our lecture of today, let me tell you some words, even if many of you might already know something because that's the 8th lecture in the series, about our project. So Strong 2020, it's really a very important European project, which is also, among other things, which are scientific, hosting this public lecture. The lecture of today, it's related to its connection between universe, in particular the gravitational waves, and physics at the extreme, and some of the activities we are doing within our program, because we are trying to put together different type of phenomena in the universe, like those connecting the particle and nuclear physics with the physics in the cosmos and in cosmology, including the gravitational wave. We have a very special speaker today, Professor Jo van den Brand, which I will introduce shortly from Amsterdam, from Netherlands. And as I was promising you, as I was telling you, I will introduce before the speaker starts our project. So here I also give you the webpage of our project, which is an international, actually an European project funded in the Research and Innovation Program. You see here the details. And the full name of the project is the Strong Interaction at the Frontier of Knowledge. And we are together a consortium which is quite important. Namely, it includes 44 participants, actually participating institutions from 14 European member states and one international European organization like CERN, and it also includes other countries like 21 other countries which are benefiting from European fundings, and 3,000 researchers from 36 countries altogether. So you see, it's really a big project. We are also offering within our projects access, so we are paying access and users to world-class facilities like accelerators, which are situated in countries in Europe like Germany and CERN and Italy. You see here the names of these infrastructures. And in addition, there is also a center, European Center of Excellence in Trento, the ACT STAR, to which we are offering access. Today's lecture, it's, as I told you and promised you, very special because it has to do with the gravitational wave observation. What we learn from gravitational wave, which have been we could recently start to observe them. So what we can learn by observing them also in relation with gravitational waves produced in objects which are very fascinating, like neutron stars. And this also initiated the so-called multi-messenger astronomy, where you can match together signals coming from different type of interactions, like the gravitational waves, and light and electromagnetic signals, like the ones which we observe with the telescopes. So there are also, this has been able and enabled by recent developments in technologies, and it's connected also with particle and nuclear physics, which is going to be actually discussed today. And it's a very big pleasure for me today to introduce not only a speaker who is expert in what has been happening up to now, but also in what will happen in the future, because we have here with us Professor Jo van den Brand, who's going to talk much more in detail and about this fascinating sector of the gravitational wave and physics of the extreme. Professor Jo van den Brand is the project director, project director of this future facility, which is the Einstein Telescope. So I invite him to join me in a live. Thank you for being with us, Professor Van den Brand. For those who want to learn more about our project, please connect here. Otherwise, I thank you once again for having accepted our invitation, Professor Van den Brand, and I leave the floor to you. But before doing this, let me tell to those who are connected and are following us, you can ask questions in our chat, and Professor Van den Brand will answer questions at the end of the lecture. So if you are curious or you want to learn something more, just write your question in the box and we shall come to you after the lecture. So please, Professor Van den Brand, the floor, it's yours.
Yeah, thank you very much for this nice introduction. I hope you can all see my screen. And let's start. So the topic of today will be gravitational waves, and I will focus on the physics that you can do with it. Of course, you can do much more on astronomy, etc., but I will talk mostly about the physics aspects of gravitational waves. Gravity is one of the fundamental forces, and it's actually the least understood fundamental interaction. If you look at the most important open questions and problems that we have in contemporary science, then they are related to gravity. For example, the acceleration of the universe, we attribute it to dark energy, but also the standard model of cosmology, it features dark matter, and the matter in the universe should be dominated by dark matter. And again, these are aspects of gravity. It could also signal a breakdown of our theory. So general relativity is the theory that describes gravity. There is a tremendous worldwide intellectual activity going on because general relativity, our best theory of gravity, is not a quantum theory. And we know that in certain important circumstances, like the creation of the universe or the end of matter in black holes, you need a combination of quantum field theory and general relativity. So people are looking at that, and string theory is an example of this. But the reality is that we don't have that theory yet, and we cannot describe these circumstances in physics. There's also a large experimental activity going on, both in astronomy and particle physics. And for example, there are detailed studies of the cosmic microwave background radiation. There's Euclid coming up, and particle physics at CERN, at the LHC, but also dedicated dark matter searches, for example, at Gran Sasso, are trying to shed light from the experimental side on these questions. Gravitational waves, they are essentially the dynamical part of gravitation. So the entire space, the entire universe is filled with gravitational waves, like it is filled with electromagnetic waves. The difficulty with gravitational waves is that they are very, very difficult to detect. Their interaction with matter and with your instruments is very weak. So you can turn this around and make a positive statement and say they are the ideal information carrier. So once they are created, they almost don't suffer scattering or attenuation. And in fact, the entire universe from the start, so like 10 minus 34 seconds after the Big Bang, has been transparent for gravitational waves. They might actually be the only way for us to directly look all the way back to the very, very early universe, to the times of inflation and the Big Bang. So I think right now is the time to experimentally test gravity, and in ways that we could never do this. The instrument that you see there in this video is one of the LIGO detectors. It's one of the big interferometers in the US. And LIGO was instrumental in detecting the first gravitational waves in 2015. In this talk, I will focus on the fundamental physics that you can do with black holes and neutron stars. And I will say a bit about cosmology, but many other topics I just don't have the time to cover today. So the first person that predicted the existence of gravitational wave was Einstein. He did this in a paper in June 1916, so more than 100 years ago. And Einstein, he was thinking very deeply about the meaning of space and time. And he realized that space and time are physical entities. So you can create space and time, you can destroy it, and you can create it in the Big Bang, destroy it in black holes, and you can stretch it, and you can send waves through it. And that gravity is essentially geometry of the four-dimensional construct that we call space-time. So the other thing that he realized in this publication of 1916 is that if you look at gravitational waves, then the coupling between gravitational waves and matter is very small. And he says it's so small that in practically all thinkable cases, it will be negligible. And it's glad that we could prove Einstein wrong, because he's almost always right. Because we, even though this is very, very small, we managed to detect gravitational waves. Another interesting thing in this first publication about gravitational waves is that at that time, quantum theory, quantum mechanics was being constructed. And the argument for quantum mechanics was that you have this nucleus in the atom with the electrons orbiting the nucleus. And the Maxwell's equation would say that if the electrons are orbiting, then they are accelerated in the circle and they would lose energy. They would radiate electromagnetic radiation and they would fall immediately on top of the nucleus. So atoms cannot exist. And you need quantum mechanics in order to ensure that that you get stationary states where actually this electromagnetic energy is not radiated. And Einstein realized that the same is true for gravitational waves, because also the electron will be accelerated around the nucleus. It will emit gravitational radiation, and you need quantum gravity in order to stabilize it. And this is, as far as I know, the first mention of quantum gravity. Here you see Brian Greene, and Brian Greene says that, okay, that if you have this structure of space-time, then you might as well grab it and shake it, and the shaking will result in waves of distorted space-time that go with the speed of light through the universe. And that is how you can get an image of gravitational waves. Now, the first one that really realized that you could do a detection of gravitational waves was Weber. He tried to do this with big steel cylinders that then later on were cooled down to low temperature, but it never resulted in clear detection of gravitational waves. Ray Weiss, a young professor in 1964 at MIT, realized that you could use interferometers to do these measurements. And but he also realized that even if you make kilometer scale size interferometers, so where you have a beam splitter here and the end mirror is here, and the distance between this mirror and the beam splitter is 4 kilometers, 4,000 meters, then you need this kind of measurement precision if you want to detect gravitational waves. So the change of the length, delta L over L, that's what you call the strain, that you should be able to detect is in the order of better, smaller than 10 to the power minus 22. And that is incredibly difficult because the ground that you're walking on is already shaking 12 to 15 orders of magnitude more than this number. So you need tremendous stability if you want to do these measurements. Nevertheless, he wrote this down, he worked it out, and he convinced the NSF, the funding agency in the United States, to fund that project. And this is how, at the end, LIGO was realized. But even after approval, it took about 40 years to come to a detection. So the first detection was made with the LIGO detectors, the two big interferometers in the United States, in 2015. And you see two black holes merging into a single black hole. These black holes that are orbiting each other, you can see them here, they each have a mass of about 30 times the mass of the sun. And if you would look at the size of these black holes, they are the size typically of the Netherlands, of a small country. And they are turning around each other with a speed of about 150 times a second. So that's faster than the mixer that you use in your kitchen. And then these gravitational waves that are emitted, so these distortions of space-time, they traveled over more than 1 billion years. And then they reach Earth on the 14th of September. They came in from the south, and you see this is what happened. And Earth was compressed in one direction, and at the same time stretched in the other direction, and that could be detected with these interferometers. Of course, the scale that you saw there is vastly exaggerated, because in reality it was tiny. These displacements were in the order of 10 minus 20 meters. So some scientific highlights on this. So here you see the two black holes that are orbiting each other, and this can take billions of years. And in the meantime, they are emitting gravitational waves. At some point, these black holes will touch and will melt into a single black hole. Now, that is the merger. It's very difficult, and you need numerical relativity to calculate what is happening then and how space-time is stretched. And then you get this black hole that is formed at the end, and it is a very deformed black hole, and that will ring down to its final state, and all the deformations will be radiated away in gravitational waves. And that's what you call the ring down phase. And then at the end, you will have a black hole that you learn about at university. It has a so-called Kerr metric, spinning black hole. Now, the couple of things, if you look at that signal here, then you see the signal is increasing in amplitude, but also the steps in time are becoming shorter, so the frequency is going up. And that is a typical chirp signal. So the amplitude and the frequency goes up. And that is how you can recognize it. If you measure the frequency and the change of the frequency, the FDT, then that gives you information about the total mass of that system, the chirp mass. And actually the maximum frequency that you detect is related with 1 over the total mass of that system. So when we saw this signal in September 2015, we immediately know that the total mass was about 60 solar masses. If it would have been 2 neutron stars, which we thought would be the first detection that we would make, because we didn't know that these heavy black holes existed even, then it would have been more than 1,000 hertz. But since it was like in the order of 100 hertz, we knew it had to be a very heavy system. The other thing is that this phase development that you see here, we can calculate in physics. It's called the Post-Newtonian Expansion, and we can calculate that up to 7th order in V over C. So these are very precise calculations using general relativity. And the other thing is that the amplitude here is directly related to the distance. So if you detect a gravitational wave and you see how the frequency dependence is, then you immediately know the distance to the source. And that is very valuable if you want to do cosmology. So this in-spiral phase, so this phase here where I said where the two black holes are orbiting together, and you describe that in this expression over here, you can look at all these components in that expression, all these post-Newtonian components, and you can calculate them precisely in general relativity, and you can compare them to your measurement. And the difference between what you measure and what you calculate is what I call a delta p hat over here. And you see in all of the cases, it is equal to 0 within the error bar. So we do not observe in this detection a deviation from general relativity, although we tested in a very new domain under extreme gravity. It was never tested this extreme before. And also all these terms have a certain meaning. For example, they describe the reflection of gravitational waves from the background curved spacetime. And that's what you call the back reaction. And these black holes are spinning. and they're returning around each other. So you get spin-orbit coupling, and you get coupling between the spins. And you can test all of that in the theory, and it turns out that general relativity for this event is describing that perfectly. Now, the merger is more difficult to describe. You need numerical relativity, but also that is in agreement with general relativity, and also the ring down. So the first test in the strong field domain that we did on general relativity was passing this successfully. But of course, when you look into this type of physics, then you also see, yeah, but how are you certain that you actually have seen a black hole? Because why? Maybe you've seen a wormhole, and you could also have the merging of wormholes or other objects like black holes that are not the ones in general relativity, but they have quantum modifications, or boson stars, or gravastars, or firewalls, or any other object, because theoretical physicists are very creative in thinking up all type of objects. And how do you know that what you have observed is really this black hole that was described by Einstein in general relativity? Now, the real answer is we don't know that precisely, and but we think these are conventional black holes because of the following. If you look at this merger phase over here, then you see you have made a black hole, but the horizon is very much stressed. So it's a deformed black hole that then rings down by emitting all these deformations and gravitational waves to end up in this spherical shape over here, or in this geometric shape. And you can calculate how fast it should do that, and at what frequency these gravitational waves should be emitted. Now, if you do that in general relativity, then you have this black region over here. So general relativity tells you within 4 milliseconds, it should decay to the final state, and it should emit the gravitational waves dominantly at 250 hertz. And now you can look at your data and see if you agree with what general relativity predicts. Now, you have to wait till, you cannot do this at the peak. You have to wait a few milliseconds until the total horizon is closed, and you really can talk about a deformed black hole. So that takes about 3 milliseconds. And then you see that indeed it is somewhere between 230 and 270 hertz that the radiation is emitted. So that's indeed compatible with the 250 hertz. Yeah, and the decay time that you see is between 3 and 9 milliseconds, and general relativity predicts 4 milliseconds. So within the error bar, again, general relativity is saying that what we observe is consistent with a black hole as described in general relativity. Now, is this completely solid evidence? No, it is not, because essentially, when you hit an object like a black hole, it will not only ring in the lowest mode, it will also ring in all kind of higher order modes. And what you would like to do to characterize the object is also measure all these higher frequencies and also the decay times of these higher frequencies. Now, with the first event, we could not do that, but we are working on collecting all of that information and trying to get also a handle on these higher order modes. Now, once we can do that, then we know whether this object is a black hole according to general relativity or not. So this is a work in progress. Another thing that you can ask yourself, that if gravity is a quantum theory, then there should be a quantum. Like in electrodynamics, there is this quantum, it's called the photon, and we always say the photon is massless. Now, the same should be true for gravity. There should be the graviton, and the graviton should be massless. Now, of course, you can ask yourself, can you measure the mass of this graviton? So assuming it would exist, can we put a limit on that? Yeah, we can do that, because if there would be a graviton, then this relation for photon is E squared, E is P times C. But for a massive theory, you have this mass term over here, and that gives you a dispersion when the waves are traveling, because then the particle cannot travel with the speed of light anymore. And you would see that in the dispersion of the gravitational waves. So we analyze that, And essentially, we derived this limit over here. So we don't know if the graviton exists, but if it exists, the mass will be smaller than 10 to the power minus 22 electron volt. Now, this was based on this single event that we measured in 2015, but this limit over here is already 10,000 times stronger than the limit that we have on the photon. So every time when you say the photon is massless, I could ask you, how do you know? Did you measure that? Because we measured it on the graviton, and on the graviton, that limit experimentally is already 10,000 times stronger. So then a while later, in 2017, the European detector Virgo was ready, and we could join the observations with the LIGO detectors. So Virgo is a European collaboration. There are 16 countries involved, more than 700 members, 129 institutes. And the detector is located in Italy. And here you see the detector in Tuscany. So it's behind the mountain is Lucca. And to the left here is Pisa, and to the right is Florence. And this detector performed the first detection in 2017. So here you see that event. And after 2 weeks of running, you see the detection in the two LIGO detectors and the detection here in the Virgo detector. And this was interesting because with LIGO and Virgo, you have the possibility to measure the polarizations of gravitational waves. And in general, metric theories, you could have 6 polarizations. And what is polarization? It's essentially you take space and you start stretching space and you wonder, how will it stretch if I start pulling on it? And general relativity is very specific about that. It says that if you try to stretch it in this direction, then it will stretch in one direction, but it will shrink in the other one. So you cannot take space-time and pull it from all the sides and stretch it. That is the meaning of this. And so we did a measurement, this event on the 14th of August, 2017. And we analyzed it, assuming that either the gravitational waves will be of scalar origin, of vector origin, or of tensor origin. And the data were very clear. There is very strong support that indeed gravitational waves have a tensor polarization, and that is the way it works. And this is a very fundamental test of properties of spacetime. 3 days later, the 17th, we saw the merging of 2 neutron stars. And this is an event in your life that you will never forget. At least I will never forget. I was sitting in the office with my colleagues over here, and we saw that there was this gravitational wave that merged, that was seen in the detectors, and then 1.7 seconds later, it was seen in 2 satellites. And of course, what the satellites see are electromagnetic waves and black holes. And you have to realize a black hole is made out of vacuum. It is made out of space-time. It is an object purely constructed from space-time. All the matter that falls in a black hole disappears in a singularity and it's gone. And the black hole is space-time. The gravitational waves are space-time and it's traveling through space-time. So everything is space-time. So you cannot see any electromagnetic signals. You don't expect that. But if you see these signals here, it is evidence that there might be neutron stars involved. And this, also from the frequencies, we immediately know that this is a merger of 2 neutron stars. Here you see the 2 satellites. Fermi is a satellite from NASA. Integral is a satellite from the European Space Agency. And both of them detected that signals within a very short time. So neutron stars are incredible objects. So they are laboratories for extreme physics. The masses are typically between 1 and 2 solar mass. So you take the mass of the sun and you squeeze it down, not to the size of Earth, not to the size of a city. And the density is then several times nuclear matter, which means that if you take a spoonful of nuclear matter, it has the weight of like the Himalaya, and it's of Mount Everest. It's very, very dense and heavy. Temperatures are in the order of up to 10 to the 12 Kelvin. But despite the temperatures are so high, you get superconductivity of the protons in neutron stars, superfluidity of the neutrons in neutron stars. And it's an extreme object. It's held together by gravity, but it does not collapse into a black hole. So it's supported by degeneracy pressure, by the nuclear repulsion. So it's a fight between gravity and QCD. And the way to describe this matter is what you call the equation of state. And there are many, many models for that. And that is what we would like to find out. What science is going on, what physics is going on, and what are the properties of these objects. Now, we could see them thanks to having 3 detectors. So Virgo was very crucial in that. And you see from the arrival times, you can do triangulation and you can tell to a point in the sky where this information is coming from, because the satellites don't know where it's coming from, and also otherwise you would have to look over the entire sky. So it took less than 11 hours until this SWAP team, a team of astronomers, found the object. It's here. So imagine a neutron star is the size of a city, and 2 of them are colliding together, probably creating a black hole. And you can find that object with a 1-meter telescope at a distance of more than 100 million light years. That is what these people did, these astronomers. And then immediately many more ones, because this gets announced to the international community, and then many other instruments are zooming in on that location, and they are making spectra and taking data. So this was an extremely exciting time. Here you see a NASA animation of the 2 neutron stars. So they are speeding up. They go with 1.5 kilohertz around each other, smashed together with half of the speed of light. And then you see this gamma rays, or these going out, that are detected by the satellites. And in the center here is what we call a kilonova. And most of the heavy elements are created in that nuclear oven that is generating all of these elements. Now, one of the things that you can do is you can compare the arrival time of these gravitational waves and of light. And you see that they have been traveling 100 million years, but still arrive within 1.7 seconds. So that tells you that they have, within this error bar, identical speeds. So we know we did an independent measurement of the speed of gravitational waves. But then these gravitational waves and these photons are falling into the gravitational potential wells of our galaxy and of the other galaxies that are nearby. And you can see that they are falling into these potential wells in the same way. And that is a test of the so-called equivalence principle. So we did that too. And the equivalence principle is the basis of general relativity. If that will be violated, and we would have to reformulate this theory. The other thing is that, as I said, the neutron stars are extreme objects. So they probably have a crust. There is superconductivity, fluidity, fluid vortices going on. What is the origin of the magnetic fields, etc. But when these objects are rotating around each other, they are deforming each other through tidal interactions. And the stiffness of the object will tell you something how it can deform. Now, this tidal deformation will affect the orbital motion. It will be imprinted on the gravitational waves. So by measuring these gravitational waves, you get a handle on this tidal deformation, and in this way on the equation of state. Now, these are very detailed calculations, all done with supercomputers and comparing to our data, and it tells you about the structure of neutron stars. Now, with one event, it is difficult to say exactly what the equation of state is, but in the way we do the analysis, if we would have something like 50 of these events, then we are very precise in making statements about this equation of state. So here you see another movie, and this is the Hubble. So Hubble also zoomed in on this object. And Hubble, so there are many galaxies that you have to go through, and then look in these galaxies where this object the size of a city is. And here you see the galaxy, and here you see the object. Here you see this collision of neutron stars. So when this is known, immediately also all the big telescopes start zooming in on this object and start studying it. And ESO, the European Southern Observatory, has many excellent instruments to do analysis on these objects. So here you see the how the light curves are changing. So these are the wavelength, and this is the object. So let's start and look at the object. You see it's blue, but after a few days, it starts turning red. Yeah? And you see that this oven is cooling down. This kilonova is cooling down. And of course, this gives lots of detailed information about this process. Another thing that you can do is that if you get electromagnetic radiation, then you can look at the redshift. And as I said, if you have gravitational waves, then it is self-calibrating, the distance, because the size of the gravitational waves is related to the distance. And then if you have the distance redshift relation, then you can do cosmology. And you can, for example, determine the Hubble parameter. So if you know something about the Hubble parameter, then you can measure this with the cosmic microwave background radiation. For example, the Planck satellite has done that. But you also can use supernovae to do this. And both of these measurements are quite precise, but they don't agree with each other. There's an 8% error between these measurements. So with one event, this is our measurement of the Hubble constant, which is not very precise. But again, if we collect something like 30 to 50 events, then we can do a 1 to 2% measurement of this and solve this discrepancy issue. So it has also consequences for cosmology. And there are many more things that you can do if you have more measurements. For example, look at the equation of state of dark energy. So with all of this, I hope to show you that you can do exciting things in fundamental physics, but also in astrophysics with these neutron stars. I didn't talk much about astronomy, a little bit about cosmology, and of course, when you have these neutron stars and colliding neutron stars, you learn a lot about nuclear physics. The last part, I would like to talk a bit about the future. So in 2020, the Japanese Kagera detector joined LIGO and Virgo. That is a detector which has 3-kilometer arms. It's built underground. So in the next runs, Kagera will also participate. And so far, we have done 3 observation runs. So the first one, where we had the first event, was from September 2015 to January 2016. And we measured 3 events in that time. And the second observation run was essentially in 2017. This is where Virgo joined at the end, and where we had this triple detection, and when we had also the binary neutron star. And then in 2019 and 2020, we ran for 1 year, and we collected many events. You can see that over here. All of this is published, and essentially with the sensitivity that we had in this third observation run, we had a detection every week. So we have many black holes, and all of that is right now published. So the papers, everything that we do is open. So when we have a detection, we give an open public alert so that everybody can follow up. When we publish, we also make our data public, and you can go to these sites. We also make our software to do the analysis public, so you can reproduce what we are doing. And we give several times, so typically once or twice a year, we give lectures for about a week so that you can learn how to do this type of analysis. So if you are interested in that, then take a look at these links. So the outlook. So this is Virgo. I think it's a beautiful detector here in Tuscany. And it's more than a simple interferometer, because an interferometer is essentially laser, a beam splitter, and two mirrors. But we have also these cavities that we use, and we have recycling of power and signal. And we do many more state-of-the-art optical techniques to do these measurements. Here you see the beam splitter in Virgo. So you see it's a sizable piece of optics. It's 55 centimeters in diameter. This red stuff is a coating that we remove once we go into operations. And here you see a 40-kilogram mirror of LIGO. So this is the sensitivity of one of the detectors. This is of the LIGO detector. So on black you see the sensitivity curve. And all of these other curves that you see here are calculations that we do on noise sources. So there are many things that can distort our measurements and create noise. And the green here is the sum of all these noise sources. And the agreement tells you that we quite well understand what we are doing and what we should work on if we want to improve things. Our understanding is maybe not as good at the low frequencies, but apart from that, it's quite good. And the biggest issue that we have is with this red dashed curve. Now that is quantum noise, because we're working close to the quantum limit. And if you use coherent light, there's actually a way to get around that quantum limit. If you start entangling photons in the different arms, then you can improve your sensitivity. And that is called squeezing, using squeeze light. So both LIGO and Virgo already implemented squeeze light, but only at the high frequency part. And we're working on right now to implement it over the entire frequency range. And that will increase improve the sensitivity. So here you see the past observation runs in 2015, 17, and 1920. We actually had to stop the third observation run due to COVID. We are here right now. This is today. And at the end of this year, we will start running again. And you see that that Virgo is quite ambitious in trying to double the sensitivity. LIGO will go to the design sensitivity. And then we run for about a year, and then we upgrade again, and then we will come back with the second upgrade. So this here you can see, for example, that this is the sensitivity in Virgo, and especially at the high frequencies, we hope to improve a lot. While LIGO is aiming at this improvement here in this line, so over the entire frequency range. Here you see people working. So these are colleagues from Virgo, and essentially working on this squeezing technique, which involves making a long, about 300-meter long, so-called filter cavity, and having high finesse in there, and using that to make specially prepared so-called squeeze light that you inject into the interferometer, and then you can decrease your quantum noise. And here you see the upgrade that we will do after the next run. We will go to mirrors of about 100 kilograms, and we will do special coatings on these mirrors. All the coatings on LIGO, Virgo, and Carglass mirrors have been done by a group in Virgo. That is the group at LMA. It's in Lyon, and they are actually the only party right now that can do this. If you look at these mirrors, so if you read in your textbook, your physics book, about an ideal mirror, this is the closest to an ideal mirror. If you take a mirror like this and you would amplify it to the size of a big city like Rome or Paris, so like 20-kilometer diameter, then the flatness of that surface is the precision of a human hair. That is the precision with which we machine these type of mirrors. So it's these are very, very perfect objects, and that's what you need to do if you want to detect gravitational waves. So then there will be a new generation. So hopefully 15 years from now, we will have an object that is called Einstein Telescope. We don't know yet where it will be built. It could be built in the border region of the Netherlands, Belgium, and Germany, but it could also be built in Sardinia. So we are investigating both locations, both sites right now. At the same time, there is a proposal which is not as developed right now as Einstein Telescope, but there's a proposal to build a new detector in the US, a project, maybe even multiple detectors. It's called Cosmic Explorer. So the length here of these arms is 10 kilometers, and this here goes up to 40 kilometers. This is underground because we want to measure, especially at the low frequencies, and this is on the surface. So Einstein Telescope is again a European consortium with more than, so right now 41 institutions involved. It's coordinated by Italy and the Netherlands. And it was approved to be on the European roadmap of future infrastructure. And here you see, if you are interested, you can go to these locations here, and you can look at the conceptual design and also the upgrade of the design. We have, of course, also publications on the science case, etc. So it's a triangle with arms of 10 kilometers, and it contains 3 overlapping detectors. And these detectors are built a few hundred meters underground in hard rock. And every detector consists of 2 interferometers. One interferometer is optimized to measure the low frequencies, while another interferometer is optimized to measure the high frequencies. So Einstein Telescope, in its final configuration, will have 6 overlapping interferometers that you have to run. And part of the optics here is at cryogenic temperatures. So if you have this, then you have here the sensitivity curve of the low frequency one, the sensitivity curve of the high frequency one, and you can merge that together to one broadband sensitivity. In astronomy, this is done very often. So if you want to measure at infrared or at X-rays, you make 2 separate detectors. And we do something similar to measure the low frequencies and the high frequencies for gravitational waves. So you see the sensitivity of these instruments, and compared to the present sensitivity. So at 10 Hertz, you talk about improvements of 5 orders of magnitude in sensitivity. And at, say, moderate frequencies, it's about a factor of 30. Now, if you are 10 times more sensitive, you can look 10 times deeper in the universe. And the volume that you cover with all of the galaxies goes with the cube. So that means you get 1,000 times more sources and 1,000 times higher event rate. So the number of detections that you will do in a year could be up to 1 million. And while right now we have a detection every week, will have hundreds per day with Einstein Telescope. The other thing is you can go to over a very wide range of masses of black holes that you can detect, and you can detect them up to distances of redshift of 100. That might not mean a lot to you, but if you look at this distance, a redshift of 100 is a few 100,000 years after the Big Bang. So that means that with LIGO Virgo Consortium at present, we can look up to maybe 4 billion years after the Big Bang, and we're looking at our local universe. But with Einstein Telescope, you can look into a region where there were no stars. And you could say, yeah, but if there are no stars, how can you make black holes and neutron stars? Now, it could actually be very crowded with black holes that could have a primordial origin, and that could have been created in the very early universe. So with Einstein Telescope, there is quite a high discovery potential to go to that region. There's a lot of other physics that you can do, but I will not go through that. Also in the future, we will have other instruments like SKA and CTA is being realized. There is the extreme, the large telescope, Euclid, etc. So we can do multi-messenger astronomy with many, many instruments. And let me conclude with showing you a picture of how it could look like. And here you see this triangle with arms of 10 kilometers, constructed a few hundred meters underground. This is a corner station. You see the arms of the 6 overlapping interferometers in the tunnels. The towers here are needed because you need to do vibration isolation. And below the towers, you have clean rooms where you can put in and prepare your components. In this complicated layout, this facility is constructed to have a lifetime of something like about 50 years, so that once you find and develop techniques to make it more sensitive, you can upgrade your facility. And so we hope to realize that, and I think many people are working to make this happen. So let me conclude with this last slide and say that I believe there is a very, very bright future for gravitational wave science. Okay, thank you.
Thank you very much for this really very fascinating lecture. And you brought us into the next 50 years, which is really quite impressive, passing from few events per year to a million of events or something like that. I see already in the chat some questions, and I'm going to read some of them for you. So there is one of the interesting questions done by Emin and Tugrul. She's asking whether there are any observation for more than two bodies.
I think in astronomy there is some evidence of free body systems, but it is also a matter of how you define it, because everything is rotating and moving with respect to everything. So for us, when we talk about a binary system, we are mostly interested to see the collision, so to see the end. But in principle, there are many objects that are rotating and turning around each other, but they are not in a phase yet that they would be a source of gravitational waves. We had a measurement about a year ago, which we published, which was kind of massive, and also there were some publications that people think that a third body could have been involved. But we will see whether this is true.
Interesting. Then there is a question which has been put forward by Davide Molina, who is asking whether one could imagine or hope to get some information regarding with the gravitational wave coming from inflation periods, so from very early universe.
Yes, that is a very, very good point. That is actually probably the most exciting part that you could discover. And we have 4 big data analysis groups with LIGO, Virgo, and Kagura. And then you have to think about more than 1,000 people, 1,500 people working on data analysis. And I only talked about the data analysis group that is looking at the collision of these binary systems. But we have a whole data analysis group looking at this type of signal, so-called stochastic signals that could come from phase transitions in the universe, from inflation, from the end of inflation, from the Qcd phase transition, etc. And we are doing our best, but so far we only could place upper limits. We could not identify. If you would have known that, because once we find that, this will be so incredibly exciting. We also looking at other things that if you have, for example, the Qcd phase transition, which happened in the early universe, at a redshift of 10 to the 10th roughly, then that could also have led to the creations of many primordial black holes. So by looking at the populations of black holes, you might also get some handle on these type of early phase transitions. So when made a statement, you can look back to a few 100,000 years after the Big Bang, then I'm only talking about these colliding black holes. But if you get an event from these stochastic phase transitions, that could be much, much earlier.
Right. And related to this, there are other interesting questions. I don't know the name of the person. It's, yeah, the nickname is Root XU. The first one I'll start with is second is if we know the age of the black holes merged. In other words, is there an age distribution of the observed events?
Yeah, what you can, once you get these black holes, what you can do is you can make, so we have about 90 right now. So what you can do is you can make distributions of that. And of course, you would like to make distributions with 100,000 events and not with tens of events that we do right now. And I think it's too early to draw conclusions on that. What you see if you look at the papers, and I put the references in the slides. If you look at the mass distributions, you also get some evidence already on some structures, which is interesting because why would there be a structure in these mass distributions? Why would certain masses be preferentially generated in black holes? So these are very important questions, but it's a good time to be a physicist right now, because right now, if you join this endeavor, you are the one that is finding out answers to all of these questions. We are trying to figure out how the whole history of the universe developed. So we have many unique instruments to do that. I think it's a fantastic time right now to be in this type of physics.
And I hope that some young people are listening so they can take this advice as a career advice. Why not? The same person has done a second question, which I'm reading it. I don't understand it, but you might. What's interpretation of the rapid increase of the cumulative events since phase 03?
Oh, okay. Yeah, that is yeah. Yeah, what happens is that if you double your sensitivity, because we are working, you could also rephrase the questions. Why are you only measuring a few months and then you stop for more than a year, and then you're measuring a year, you stop for 2 years? Why do you do that? Why don't you keep on measuring? Now, the thing is, we see opportunities to increase the sensitivity, let's say, by a factor of 2. But if we can do that, we can look a factor of 2 deeper in the universe. We get a volume that goes with the cube, that is a factor of 8, more events in the same time.
Right.
So that what you see there is the essentially that we are improving our sensitivity. So when we come online again, you will again see a much steeper slope, and hopefully in a year we get many more events, like hundreds of events, maybe a few hundred.
Thank you very much. Then there is a question from Kristi Mitrofan, who is asking why there is a different arriving time between the gravitational wave and gamma ray burst of 2017 event. Does this?
Yeah, so the difference in arrival time was 1.7 seconds, and the gravitational waves arrived first. So what you have to realize is that the gravitational waves are coming from very dense regions of matter, which are accelerated hugely. So imagine that you have these two neutron stars that are colliding. Then the gravitational waves are generated in the center where all this matter is colliding and is accelerated. And since that matter is transparent for gravitational waves, these gravitational waves come out first, while the electromagnetic waves come a little bit later. And that probably tells you a bit about the size of these objects and things like that. And but it's about that. So the nice thing about gravitational waves, that if you have enough sensitivity, then they are already generated when the two neutron stars are in spiraling. They are not touching. So there's no emission of gravitation of electromagnetic waves, but the gravitational waves are emitted. So with Einstein Telescope, we think that already for certain systems, more than a day in advance, we will see the gravitational waves. We can tell astronomers, you have to look at that part in the sky. There is this system, it's emitting gravitational waves, and tomorrow at this time, it will merge, and you should see the explosion. So please point your telescopes to that. And we probably even can tell them this is an interesting system because it has these masses, it is spinning like this, and it's special. So look at it.
That's absolutely fantastic, and actually helps me to ask the next question, which was put by Joris van Heiningen, who is asking, what do you think is the most challenging technology for the next generation gravitational wave detectors?
Oh, that is a very difficult question. So what we are trying to do, so I already showed you the sensitivity curves. And you see that the challenge is probably at the lower frequencies, because already at 10 hertz, I said you have to improve your sensitivity by 5 orders of magnitude. And we would like to go even lower in frequency. So we go underground, we make it cryogenic, but it's really, really difficult. And probably so many technical challenges are there that we have to be extremely innovative in order to overcome that. So I think that the starting at maybe 50 hertz, from there on, it's probably all laser power and we can do it. But at the lower frequencies, that is where the challenge is. And it could be in the controls, in the measuring and keeping all the things aligned and quiet. Could be in the vibration isolation. So it could be in the surrounding seismic motions that are exciting vibrations. It's really difficult.
So there's a lot of things to do for the next generation.
Yeah, but also I think the nice thing about that is that you develop many technologies to cope with all of these problems that could be valuable for industry.
That's you did a very good point. And if you want just 1 minute to tell something about this, because it's something which we are always asked by people, what this is producing. So that would be interesting.
Yeah, there are already many spin-offs from gravitational wave science. So the purity of the optics that we use can be used in other optics fabrications. But for example, if we steer the mirrors, we apply very small forces to do that, not in order not to disturb it. So nano forces. Now there is there's a discovery by in the medical sector that if you use nano forces on stem cells, you can get these stem cells to differentiate into bone cells. And now there is a company coming from gravitational wave science together with people, medical people. It's called NanoKick, and they are creating now with this technology bone cells. So that if people, for example, step on a mine, on a landmine, where they would lose maybe a leg, you could grow these bone cells, and you would be able to help them and maybe do something about that. So that was something that nobody could anticipate, that this would come out. There are other sensors that are being used to measure vibrations. So the biggest seismic surveys right now, geophysical surveys in Europe, are using sensors that came from this field.
Fantastic. Oh, meantime, another question popped up. Why third generation gravitational wave detectors will be able to be sensible to low frequency signals?
Yeah, because we try to construct them that way. We make them in a way that we put them underground, because typically if you measure seismic vibrations underground, it's about a factor of 1,000 less vibrating than on the surface, because many of these vibrations are made by humans, by cars, by windmills, by wind blowing, etc. So going underground makes the environment much more quiet and more stable in temperature and things like that. So we construct them in a way, and we use heavier test masses because it's much more difficult to make noise on a heavy system than on a light system. So then we improve our vibration isolation. So we take this into account in the design.
Thank you. Thank you very much. And thank you really for this fantastic journey into the gravitational wave phenomena and future of these gravitational waves. And before closing, I'd like to ask Susanna Bertelli and Deborah Vivaretti to join us in video because they were well helping in organizing all these activities. So Susanna Bertelli, who is the head of the Education and Dissemination Office of Frascati National Laboratories. And Deborah should be somewhere around from the service. And yeah, so
here she is.
Hello, Deborah.
Hello.
So our fantastic team from the Frascati National Laboratory. I also thank very much Piet Mulders from Holland, from Netherlands, who is colleague with me in the dissemination board, who helped organizing all this lecture. And last but not least, I thank very much to all of you. There are many thanks in the chat box. And last but not least, of course, I thank to Jovan den Brand for this absolutely wonderful, clear, and fantastic lecture on the gravitational wave and physics at the extreme. So thank you all. Have a nice evening. Take care of you. And hopefully we can meet you in Frascati sometimes soon, as well as everybody else.
Okay, thank you.
Thank you.
Thank you.
Bye.